shifted from the earlier day. So we will have a bit short lunch break. The lunch break will be only 1.5 hours. And then there will be additional talk which was shifted from the earlier day, starting at 2:10 by Asli Sudbo. And then the other talks shifted a little bit correspondingly. Then just in order to be able to accommodate this tough schedule, the time, please be on time, so today is just a kind of
Okay, so let's start. I want to start by first thanking the organizers, especially Igor, for bringing us all here together and giving me the opportunity to give a talk here. I also want to thank everybody in the audience for excellent talks we already heard and for being willing to bear with me and listen to what I have to say. I also want to say that I'm really glad that Joel gave his talk before me. So he is one of the founders of the field. I'm a newcomer. So what I'll tell you today is actually going to be somewhat orthogonal to what he told you. It's not a mainstream direction of research in this field. It's just something which I started doing when I came into this field. And that's why, in some sense, you're my test audience. I don't have a chance actually to tell to anyone about what this is all about. But I very much hope that you'll like what you'll hear. And I hope to hear some feedback about what you think about it. Another thing which I want to add before I go to my first slide is, for the purpose of my talk, I'll define topological insulators in a way which is more general than what Joel had in mind. He had in mind a specific time universal invariant system in 3 dimensions. He called it topological insulator. But I will call topological insulator the whole variety of different systems, of which this is just one example. And for me, integer quantum Hall effect is also a topological insulator. So my definition of topological insulator is a little bit more broad than what Joel had in mind. And so now I can go into what I will tell you. So first, here is a definition which I think Joel mentioned at some point. I don't know if everybody would agree with this, but I would say that at least non-interacting topological insulator is a free-forming system with kind of an unusual band structure, which is characterized by topological invariance. So I think people would agree with this. What is interacting topological invariance is a little bit less clear as interacting topological insulators. It's less clear what it is. Actually, I heard that Sentil once said, like Tolstoy said something about some people might remember this better than me, happy family are all happy in the same way, and happy family are happy in different ways. Same way here. Non-interacting topological insulators are all the same, but interacting topological insulators are all different, and they're interacting and topological in their own way. But so, what I'll tell you though is I'll tell you about a method to study topological insulators, which is distinct from what you heard from Joel. It's a method of single particle Green's functions. It turns out it's been around for quite a while, and I'll try to tell a little bit about the history, but it was not used by people studying topological insulators. And this method allows you to reproduce all the known results about non-interacting topological insulators, but it also allows you to make or to understand something about what happens once you turn on interactions. And so one of the goals of my talks, which I'll mention at the end, is to explain what happens once you have interactions. Most of what I'll tell you today is, it's published, at least it's in the archive, about a month and a half ago in this paper. Also, some of it is still unpublished work together with Andrew Essen. I noticed that Andrew was also involved in Joel's work. So he was Joel's graduate student who is now a postdoc in Boulder. Joel mentioned him prominently, and I think he was involved in the work which Joel talked about in the second half of his talk. And so he's also involved in this work, and so even though he's not here, his spirit is here. And also some of it is based on discussions which I had with Andreas Ludwig. So not all of what I'll tell you today is published. Okay, and also I'll spend some part of my talk kind of giving you some sort of history, at least my take on this history. Okay, so let me start with non-interacting topological insulators. As I said, non-interacting topological insulators are free-Fermi systems, and so Hamiltonian for them is remarkably simple. It's just a linear combination of creation and annihilation operators with some coefficients, hij, which is some matrix, and ij can label sites on the lattice, but can also label spin. If you have some other degrees of freedom, it also labels those other degrees of freedom. And so this is all there is to it. So you might say it's a completely trivial system, but The thing about topological insulators is that they happen to be band insulators of a very special type, very unusual type. And my plan is now to maybe talk a little bit about this on the example of integer Hall effect, and we already heard similar things from Joel and also earlier from from one of the talks earlier this week. So some of it will be a repetition, but I hope it will be just my take on this. So let me first look at some kind of trivial band insulator. So suppose I have a particle hopping around on a lattice. This is a square lattice. This is the Hamiltonian. So particle goes from one side to another, from one side to another in the vertical direction. And my example is two-dimensional, although we don't have to do it in 2 dimensions. Classical emission conjugate here. And so we know how to compute the spectrum of this guy. This is the spectrum as a function of 2 momenta. And let me plot the spectrum in the following way. I'll plot here the momentum along the x direction. And then for each value of kx, I'll plot all possible values of p when ky goes from, let's say, minus pi to plus pi. So for example, if kx is 0, then this term is minus 2t. And if ky goes from minus pi to 2 pi, this varies between between minus 2t and plus 2t. So the whole thing varies between 0 and minus 4t. And this is, so when kx is 0, this is all possible states I'm getting as ky varies between minus pi and pi. But if kx is pi, then of course I'm getting these states. And so altogether I get this picture. So these are all possible states labeled in this funny way with kx, which I get for this kind of system. And let me emphasize that it does not matter what kind of boundary conditions I impose here at the boundary. I'll still get this picture. For example, if my boundary condition in the y direction are periodic, well, that fixes some allowed values of ky. For the thermodynamic limit, they all kind of fuse together and just continuous range of ky's. So that's pretty much it. If my boundary here is hard boundary, then it's actually slightly different values of ky which I should take, so that my wave function would vanish at these endpoints. But in thermodynamic limit, again, it doesn't matter. It's still some range of ky's between minus pi and pi. It's just that the discrete points are slightly different, but in thermodynamic limit, they all fuse into the ky ranging from minus pi to pi, and this picture is unaffected. But now, suppose I turn on magnetic fields. So obviously, I'm driving at integer Hall effect, and here's a really fun exercise, which all of us know how to do, but I haven't done it until relatively recently, even though I should have maybe. Let's turn on magnetic field, and in this example, I put 1/3 flux through every plaquette, and this is the hopping, let's say, to the right, which is given by these phases, and the hopping to the left would be complex conjugate of these phases. And let's calculate in the same way, solve for the band structure, let's say with periodic boundary conditions in the y direction and also in the x direction. And well, it's not that difficult, you can do it. It's an example of one state which goes into a Hofstadter butterfly, but butterfly has many states, many fluxes. Here I have a flux 1/3 of flux quantum going through each plaquette. And so as a function of kx, here are my energy levels. And so altogether, as kx varies between minus pi and pi, they form bands. In fact, there are 3 bands here. Lowest, second excited, and first excited, and second excited. These are what happens with lambda levels on the lattice. And well, they just look like bands. So there's nothing special, except maybe they have a slightly different shape from when I had no magnetic fields. Interesting thing happened though, if I put hard wall boundaries. So you put hard wall boundaries, and then again you calculate the band structure. This is actually an honest calculation. I didn't invent it. It's not drawn by hand. It's a Mathematica, calculating the band structure of this thing. And you see these additional interesting energy levels, which actually sit in band gaps. And of course, these are nothing but H states. You can see them. So there's 2 H states here, 2 H states here. In fact, one lives on one side and the other lives on the other side. So I mean, these are just energies. You see that there are energies in band gap, but you can also argue that the wave functions corresponding to these states are localized along the edges, and they're propagating along the edge. So these are the famous H states. So if, for example, if I place my Fermi energy somewhere between 2 bands, then all the transport which may happen will happen on the edge, and that's what leads to integer Hall effect. Okay, well, that sounds really great. Well, so now how do we know that there are these H states? Well, I put it on the computer and solved it, and I've discovered there are H states. But I'm going to claim, actually, that it doesn't matter how I put this boundary. So in the computer, I put this as a hard wall boundary. The wave function has to vanish in it. But I could also make a soft boundary, maybe like increase the potential at the edge. Still, I'm claiming that there would be exactly the same H states. Maybe the shape of these curves will change, but they would still be 2 curves connecting these bands. So there's an old argument due to Laughlin. I'll just sketch it very briefly. Although I'm sure that everybody here knows about it. Imagine that we have a quantum Hall system which has a shape of a disk, and I create a flux going through a point through the center of this, and I increase this flux from 0 to 1 flux quantum. Increasing the flux through my system creates, obviously, an electric field circling around this flux. Electric field going around the circle, because it's a quantum Hall system, creates an outward current in the perpendicular direction to the electric field. Yeah?
I have a question. Why do you have two H states? You have the speed.
Well, because I have two edges.
Oh, it's just the H's.
One goes in one direction on one edge, and the other goes.
So you don't
on
have the pair of.
No, it's just quantum Hall. So I had two edges. One edge in this direction on one edge, and the other on the other edge. Okay, but going back to this geometry, so I increase the flux to 1 flux quantum, and that creates a radial current if this is a quantum Hall system. And but on the other hand, once the flux is equal to 1 flux quantum, and if it goes through a point, that's like having no flux whatsoever. And that means that the new system should also be, or the new state of the system should also be the ground state of the system. But now we had some current flowing to the edge. So this current deposited the charge somewhere on the edge. Where did it go? Well, it went into those edge states. And so that's a general argument why edge states must exist due to Laughlin. Now, of course, it relies on knowing that sigma xy is non-zero. And actually, for this argument to work, it has to be an integer times z squared over h. So you need to know this. And that can be glimpsed from the work of Thouless, who in 1982 with his collaborators showed that sigma xy in such a system, particles in the lattice, can be given by this formula, which Joel also showed. I guess it's like Jordan number calculated out of block waves, which are solutions of the problem of particles hopping around on this lattice. By the way, without a boundary. So this, you don't have to have a boundary to do this calculation. And so this integral happens to be a topological invariant, integer times 2 pi I. That integer is a number of field lambda levels. And from here, it turns out that sigma xy is e squared over h times an integer. And so we can connect that with Laughlin argument. And finally, I realized that the fact that we have this kind of topological invariant leads to quantized Hall conductance, leads to Laughlin argument, leads to H states. So that's how usually people derive H states. But now, the question comes up right away if there are any other topological insulators. And it's kind of interesting to look at the history of the subject, because the history is not that old. So I've already been around, so I kind of can try to see at least my perception of what was going on in all these years and why these new topological insulators, which Joel talked about, were missed. So people definitely noticed quite a while ago that two-dimensional px plus ipy superconductor in some sense is like quantum Hall effect. I mean, it's a superconductor, so it's not an insulator, but usually we understand these things that the Bogolov-Dejean equation for the quasi-particles in this superconductor is kind of like a free Fermi system. You know, there's a Bogolov-Dejean Hamiltonian. You can treat it as a topological insulator also, except, of course, it's not an insulator in the sense of no electric current. It's an insulator, for example, in the sense of heat. Whatever Bogolov particles transport, it would be an insulator, because there's a gap towards creating Bogolov particles. And so this kind of Q-based superconductor, which Strong's inversionite might be, is a topological insulator with respect to these Bogolov particles. But and so the question would be, well, why is it a topological insulator? Well, we know quantum Hall is a topological insulator, but in other words, topological insulator means it has those H states and everything. But people always say, well, you know, quantum Hall is a very special system. Like I was taught this in graduate school. No other system does that. If you put boundaries and suddenly there are H states. Only quantum Hall is very special. Thouless explained why. But then this this superconductor comes into play, which kind of has the same feature, also has H states, with Bogolov particles moving along them. And you could ask, so what's happening here? And people said, wait, this is just quantum Hall effect. It's 2D, right? So it's kind of superconducting counterpart of quantum Hall effect. So don't worry about it. It's no big deal. It just happens to be quantum Hall effect. But there are other examples also. So Shuch and Zhen in 2001 gave an example of 4-dimensional quantum Hall effect, which is clearly kind of different from what we did so far, because it's in 4 dimensions, not in 2. And well, what people said, it's 4-dimensional. We don't live in, well, string theorists, right? We don't live in 4 dimensions, so why should we care? But then there was another example. It was noticed already in 1978 by Schuch, Riffer, and Higger. There are some kind of interesting soliton states in 1-dimensional chains. If you look at this, this is actually also a topological insulator in the sense of H states. But again, this was kind of ignored. Well, okay, it's in 1D, very special system, not directly related to quantum Hall effect. So people were not really trying to look at all of these on the same footing. And the situation really changed when Kane, first of all, realized in 2D you have this new type of topological insulators. But that, I would say, wasn't even the the big kick, but the kick came when Joel, together with Leon Balance, and also independently came with Dan student Fu and Mele, realized that this also works in 3D. So suddenly, it was the first time when we had something which behaved just like integer monopole effect, but in 3D. And experimentalists like 3D. So that kind of told people that there is something more going on, not just one topological insulator, not just integer monopole effect, but there are other examples. And so at that point, obviously, maybe it's a time to step back and ask, well, it all sounds great, but is it all? Do we know? Are we sure that these are all possible examples? Maybe there are more. And, well, here I should say that turns out that all possible topological insulators, at least in some maybe sense, can be classified. And everything which I showed you so far are all examples of that classification table. But the classification table is much bigger. Not all entries in this table are easily physically realizable. But in order, as a theorist, maybe you want to understand all possible ways to make topological insulators before to start thinking about one particular topological insulator. And so it turns out that the classification of all possible topological insulators was already understood in the 90s, but in a different disguise, in the disguise of classification of random matrix series by Allen and Zinbauer. And only later in the 90s, I mean, in the last few years, actually, people understood, mostly maybe by efforts of Andreas Ludwig and his collaborators, that that same classification also applies to topological insulators. So basically, what we need to pay attention to is what kind of matrices Hij we have here. These matrices could be just generic, or it might have some symmetries. So one possible symmetry is a time reversal symmetry, which on the level of this matrix should be imposed according to this equation, where UT is also some matrix. So, you complex conjugate H, and then conjugate it with UT and go back to H. And UT is a matrix which can be, well, UT times its complex conjugate can be either +1 or -1. In fact, it's -1 when we have spin 1/2. So in the presence of spin orbit coupling, you always get -1 here. But it could also have +1, for example, if we have spinless particles. So time reversal invariance, if it exists, can be imposed in two different ways. And then there's another symmetry, which is a more subtle symmetry, particle-hole symmetry, which looks kind of like time reversal, but with a minus sign here. And that symmetry is always present in superconductors, for example. So all Bogodov-Dejean Hamiltonians, by default, have it built in. But not everybody who has it is a superconductor. There are systems just of electrons moving on a lattice constrained in a certain way, which do have this symmetry. And finally, there's a third symmetry, chiral sublattice symmetry, which actually can be thought of as a combination of these two. So if you first apply this guy and then you apply this guy, you can convince yourself that sigma is kind of like a product of UT, UC star. And so what it tells you is that if those two symmetries are present, the third one is also present automatically, because it's a combination of the first two. But if one of them is present, then the third one cannot be present, because if it is present, then the second one will be present also. And finally, if none of the first two are present, the third one can be either present or not present. If you combine that with the fact that these two symmetries can be imposed in two different ways, either +1 here or -1, if you count all possible ways to impose those symmetries, you get 10. And these are 10 symmetry classes of Allen and Zinbauer. So here they are. So this is how those symmetries are imposed. Plus or -1 here refer to, so if we look at T and it says -1, that means T time reversal is imposed in such a way that this product is -1. So maybe, just to make sure that I'm connecting with what those who haven't seen that before, what you already know, that, for example, in the presence of spin-orbit coupling and spin 1/2, time reversal involves flipping of the spins, multiplying them by sigma 2 Pauli matrix, and sigma 2 times sigma 2 star is -1, and that's where it comes from. Why it's -1 when you have spin-orbit coupling. And so depending on which symmetry you have present, and whether they're with minus sign or +1 sign here, you get 10 possible classes of Hamiltonians, which Zinbauer, back in '96, called by these letters. These are very strange letters. Many people who don't work with these classes complain because these letters, they sound very mathematical. They're not connected to anything. They're connected to some kind of classification of symmetric spaces and in some branch of mathematics. And Zinbauer, who was familiar with these, like these names. Now, as a physicist, when I first came to this field, I wasn't comfortable with these names. But on the other hand, we do have 10 classes, and I don't know what other names we can come up with. We can call them class 1, 2, 3, all the way to 10, but then it's hard to remember which is which. We could come up with some other names, but in the end of the day, you just learn what these classes are, and then somebody says class D, and you know exactly what they're talking about.
Excuse me. I'm not familiar with this stuff. What is the ABC? Is there any particular meaning why some is called A and some is called B?
Well, so the names are drawn from some field of mathematics. So without going into that field, I will not be explained why these names were invented. And so I suggest what we'll do instead. I'll just say, these are the names. You know, I could have called them John, Jane, and so on. You know, just some labels I assigned to these classes, which are now accepted in the field. Just I was coming here today in the morning, I was thinking that, I don't know if it's a good analogy, but, you know, Ramanujan, a famous mathematician, he's known that for every integer number to be his personal friend. So once you go into this field, each of these classes becomes your personal friend. And you don't have to be as a genius like Ramanujan, because there's only 10 of them, but there's infinite number of integer numbers. And I'm going to tell you which representative systems belong to different classes, and you'll recognize those representative systems.
Does dimensionality enter in the context of topological isolation?
It'll enter later, but right now it doesn't matter what dimensionality I have. So each class could be in different dimensionalities with consequences. But right now it's just 10 classes. And so here are various examples. For example, integer quantum Hall effect has no symmetries, and so integer quantum Hall effect is class A. I mean, I could have just told you integer quantum Hall effect. But, you know, I can maybe come up with something else, which will also be class A. So it's maybe better to say class A. When I say class A, I usually mean integer quantum Hall effect. So modern topological insulators with spin-orbit coupling, the ones that Joel talked about, they're class A too, because they have time reversal invariance imposed with a -1 sign due to spin-orbit coupling. So Schrieffer-Higger systems, which were topological in 1D, they belong to class BB1. P-wave superconductors, PX plus IPY superconductors, they're actually in class D. So every time I say class D and I talk to somebody who knows what I'm talking about, they know that I mean strontium resonate, for example. Conventional S-wave superconductors actually belong to class C1. Phase B of helium-3 are actually class D3. That's an interesting realization, which was only noticed recently by Ludwig and his collaborators. Okay, so we have all this wonderful...
Can you go back to slide?
Yeah, all right, we'll go back
So the question, so in the parentheses, that indicated the property of the group, right? Like,
well,
what about a BDG?
A BDG means Bogolov de Gens. So that means that they all realize in superconductivity. These are titles which John Bauer gave to these classes, and it has to do with random matrix realization of them, and also in what kind of systems they could be realized. So all of these 4 guys at the bottom here, they're all superconductors. These guys are not superconductors. They're just usual electrons moving around without any superconducting pairing.
I'm very sorry to interrupt, but superconductors have particle hole symmetry rule, and this Hamiltonian, so you should have terms like A dagger or something like that.
Yeah, but particle hole symmetry is present. So this symmetry is always present on every Bogolov de Gens Hamiltonian. That can be checked. All of them, because of this Bogolov de Gens structure, satisfy this. Okay. Yeah.
So you have a time reversal particle and chiral, and then you indicate this label TCS.
Right.
Are there any one-to-one correspondence?
Yeah, well, so this is time reversal. So these are different symmetry classes. This symmetry class has no symmetries, neither C, T, nor C, nor S. This one has only T. C and S are not present, and T is imposed with +1. That means time reversal invariant system of spinless fermions, or integer spin fermions. These are time reversal invariant systems with fermions of spin 1/2 with spin orbit coupling. These are more complicated systems which don't have T and C but have S and so on. That's what this table means.
You said superconductors have a particle hole symmetry.
Yes.
How we see
So all of them have C on imposed in different ways.
either +1 or -1.
Either +1 or -1.
Thanks.
Right. But notice that not only superconductors have C. There are 2 classes with C which are not superconductors. Okay.
Do you know where the non-centrosymmetric superconductors
Well, so
they fall
you
into
can
stuff?
add space groups, and then these classes will split into subclasses if you add those. And I don't want to talk about this today, but you could, and this was studied. That's additional symmetries which you can impose, which also have effects. But right now, I only talk about things which are independent of whether even you have translational invariance or not. It's just this very global symmetries you can impose. Okay, and so it turns out that there's this table which was worked out. Some people call it periodic table of topological insulators. It was worked out by Kitaev and independently by Ludwig, Rio, Schmider, and Forosaki in 2009. And this table is taken from the paper of Ludwig and collaborators. So the way you read this paper is the following. So these are symmetry classes, and these are whether they can or cannot be topological. So, for example, let's take integer quantum Hall effect. It's in class A. And so if we look, and this is space dimensionality. So if we look down to 2, it says Z here. That means class A topological insulators are characterized by integers. And these integers are sigma xy for integer quantum Hall effect. Notice that integer could be Z in any even dimensional space, but not in odd dimensional space. So for example, Zhang talked about 4-dimensional quantum Hall effect. It would have lived here, but in 3D it's impossible. Now, Su, Schiffer, and Hicker, they talked about a system which was actually in class either BD1 or A3, and this one can be topological in one-dimensional space because it has this number Z by which it's characterized. Now, two-dimensional P-wave superconductor, such as PX plus IPY superconductor, is can be topological in 2D, and indeed in 2D, this superconductor is in class D, and is characterized by an integer Z, which actually that integer was already identified by Volodik in the 80s. But so, exactly which integer you talk about when you talk about the superconductor, it's some winding of the Anderson spinner in the superconductor. Okay, but so, one interesting discovery which was made by Ludwig and his collaborators is that phase B of helium-3, which belongs to group class D3, actually is characterized by number Z in 3 dimensions. And so then the next question is whether that Z is equal to 0 or not. And so it turns out it's not 0, and that means that helium-3b has H states, which apparently, from what I understand, were completely missed in the literature before. It's a new discovery that there are H states, essentially Bogoliubov particles moving around helium-3b.
No, they were known, but they were not known to be topological. They were discovered in 1980.
Ah, I see. Okay.
A paper by Svignagel and Buchholz. Even the direct column structure was in that paper, but they were not known to be topological.
Yes, in other words, you can add to the water and other things, and they'll still be present. Now, as far as these modern topological insulators, they are in class A2, and they're characterized by invariant Z2. Z2 is this precisely this invariant which takes values or either 0 or 1, and not just any integer. And that could be in 2 or 3 dimensions, and in particular the topological insulator Joel talked about sits in this little square. Okay, now
in 0 dimensions.
you can even think of topological insulators in 0 dimensions, and this will come up later. So you'll see what this means. Huh? There will be no H theory there, but you'll see what it means. So one thing which bothers me a little bit is that I already talked for about 25 minutes, and so far I've only given you an introduction. Only now I'm beginning to tell you something which is not quite introduction anymore, although it's still introductory. So it turns out that for the general theory of all these topological insulators, chiral symmetry played a special role. Systems without and with chiral symmetries are extremely distinct from each other. Literally, out of those 10 classes, 5 have chiral symmetry and 5 don't, and they're completely different from each other. And so I'd like to describe for you what chiral symmetry is on the examples, because it's kind of not as intuitive as, let's say, time reversal invariance, which we tend to understand more. So the simplest way of realizing chiral symmetry is a particle hopping on a bipartite lattice. Like, for example, in one dimension, I have a particle which moves along a line from one side to another, and each side can be thought of as either even or odd, and hopping can only occur from an even side to an odd side. And then if I define a matrix sigma, which is +1 on even sides and -1 on odd sides, it's very easy to convince yourself that it satisfies precisely this property. In other words, if I change the sign of creation and annihilation operators sitting on every even sides, but not touching odd sides, or maybe the other way around, on every odd sides, but not touching even sides, because here, operator on an even side talks to the operator on the odd side, the whole Hamiltonian will change sign under this operation. And so that's what it means to have chiral symmetry. And so such chiral systems, they satisfy a number of very interesting properties. For example, on all energy levels, single particle energy levels of such system come in pairs. For each state E, there's a state minus E whose wave function, the wave function here is psi, the wave function here is sigma psi. That simply follows from this property of this matrix H. So these are kind of single particle states which I can then fill with fermions. So for each state E, there's a state minus E. If there are any states at 0 energy, which actually are going to be my H states, then they satisfy the following property. It's also very easy to show. It takes about maybe 1 minute to show that they either satisfy this relation or this relation. These are called right zero modes, and these are called left zero modes. And the difference of left and right zero modes is actually some sort of a topological invariant by something called Atiyah-Zinker's theorem. Although in this example, I know how to prove it, at least physicists prove it in almost one line, why this has to be a topological invariant.
Can this generalize to the case with off-diagonal tunneling, introduce large sigma?
What do you mean by off-diagonal?
So this only works when you have tunneling between these labels.
Right.
But if you have like a
Next nearest neighbor?
next nearest neighbor largest in a more realistic models,
So-
you generalize to introduce large sigma.
Yes, so if you have tunneling to the next to nearest neighbor, this will not work. Although if you have tunneling to the next nearest neighbor, this will work. So important thing, you should be able to color your sites into red sites and blue sites. And tunneling only happens from red sites to blue sites, and never from red to red and blue to blue. And then you have this chiral symmetry. That's actually a definition. So, in fact, because of this, it's kind of hard to realize these systems in condensed matter physics, but in some sense, it's actually easy to do it in cold atoms. And some of the things we're working on is thinking about realizing this with cold atoms. Okay, and now why do I...
Does that apply only to the discrete systems? You do not have any continuous space analogy of that because you need a bipartite something like that.
Well, no, there is a continuum analogy of this. So if you go to the continuum limit, for example, in this one-dimensional system, you obtain some sort of, well, kind of like a 1 + 1 dimensional
Then
Dirac
you
equation.
have to
And
change
there's
your
an
language because you are explicitly referring to...
It will be some, in the continuum language, will be some symmetry, some matrix which you conjugate with your Hamiltonian which changes sign. But on a discrete level, that's what it means to go from one set of sites to another on bipartite lattice.
Isn't this in the continuum limit the current place proportional to the momentum simply in this case?
Well, sure. So, if
Yes, so that gives you the plus minuses here of left movers and right movers.
but let me just tell you this. In this one-dimensional problem, and the continuum limit becomes simply 1 + 1 dimensional Dirac equation, which has chiral symmetry in the sense how high-energy people understand it. Sigma is what is called gamma 5.
Yes.
So you can just check that.
Yes, I think it maps in the continuum limit to this model by Jackick and Revy in 76 on massless direct fermions coupled to scalar field with two degenerate vacuum states.
Well, but here I don't think that. In my particular example so far, they're not even coupled to anything. They're not even coupled
Well,
to
you
anything.
had you had a different sign change for in your
Well, I just have fermions moving on some given lattice. So if you think of these hopping T themselves as fields, then you start coupling this to external fields. You can also look at that, but in this case, it's just particle moving on some given lattice, so it maps into a massless Dirac fermion. That's it. Okay, but so the reason I brought up those chiral systems so prominently is because it turns out that systems with chiral symmetry can be characterized by an integer topological invariance only in odd spatial dimensions. And those without chiral symmetry can be characterized by integer topological invariance in even spatial dimensions. And that's the reason why integer Conoff-Hall effect can be only in even spatial dimensions. It doesn't have chiral symmetry. And that's why Higer, Schiffer, solitons only live in odd spatial dimensions, because they actually do have chiral symmetry. And so you can see this here. So I labeled all chiral symmetry classes, those with chiral symmetry here, and those without chiral symmetry, they sit here. And you can see, for example, well, this guy is without chiral symmetry, so it's Z and even. This guy is also without chiral symmetry. And look at Z in 0, 4, 8 dimensional. Let's ignore Z2 for the purpose of this. Z2 is an extra thing, which I won't actually talk much about. But you see, the Z occurs on even spatial dimensionality. Or class D, which also non-chiral, that's a P-wave superconductor. That's Z in 2 dimensions, 6 dimensions, 10 dimensions, and so on. But chiral classes, such as BD1, it's Z in 1 dimension, Z in 5 dimension, Z in 9 dimensions, so that's only in odd dimensionality. Okay, then there are also the Z2s, which come kind of tied to the Z's, but that's a separate issue, which I will not bring up, because somehow Z2 in some sense follows from the existence of Z in high dimensionality, as Shichen Zhang first pointed out. And so it's clear that if I want to construct some kind of general theory, it needs to distinguish between odd and even dimensional space, and between chiral and non-chiral topological insulators.
Just like, could we go back one slide? Just
Okay.
So just like in the mind, so it said that Venus superconductor doesn't have chiral symmetry. So
What doesn't have chiral symmetry?
Venus superconductor doesn't have chiral
Yes.
symmetry. For instance, like in the Kitay's honeycomb lattice, you can sort of map it to a B-wave like Hamiltonian, like with the gen, like Hamiltonian. This is defined a honeycomb lattice. It has sort of the sublattice symmetry like you just described. So it sort of has a chiral symmetry built in it, and it can be classified in 2 dimensions.
Yeah, so I have to say that I haven't looked into it, so I cannot give you right away the answer, but maybe it has something to do with the fact that to be on abelian, you also have to turn on magnetic fields, and I'm not sure how you do it. You might actually break sublattice symmetry in this way. That's my first reaction.
Okay.
That's probably what happens. But if you like, we can look into it after my talk. Yeah, so without magnetic field, it's actually not in class D, I believe. It's in some other class. So, let's see. Chiral and chiral system, yes. But so finally, I'm coming to a place where I can start telling you something new, which wasn't known until recently. So all these topological invariants which characterize these insulators, as it turns out, can be constructed out of Green's functions, including the ones which Joel mentioned in his talk, although he wasn't constructing them out of Green's functions. And it's a very interesting piece of information. So let's first look at non-chiral insulators. We kind of have a more intuitive understanding what they are. For example, integer monopole effect or PUA superconductor in 2 dimensions. And so I'm going to approach them in the following ways. First of all, I want to be in even dimensional space. And I'll introduce big D, which is space-time, little d plus 1. I want to kind of fix this notation once and for all. And so my big D is going to be odd, and my little d is even, because I'm in even dimensional space. And so then I can construct the Green's function, which for these non-interacting systems is trivially given. It's just this expression. And now, if my system is translational invariant, and I will talk about translational invariant systems mostly, I can go into the momentum representation, and then indices ij gets replaced by k, and then there's also some leftover indices ab, either basis within my Brillouin zone, or maybe spin and other things. They're still left. So it's still a matrix, but it's a function of momentum. And then you can think of this Green's function as a map between frequency momentum space onto the space of matrices. Now, these matrices are some generic matrices, and so these maps are known in odd-dimensional energy momentum space, or frequency momentum space, so big D is odd-dimensional. They are known to be characterized by an integer z. And this z can be constructed. There's an expression for it. It's right here, which maybe some of you, well, you might have seen it before. It's a very common expression. You can construct it any time little d is even or big D is odd out of the Green's function. Okay. And so I should tell you that first of all, so what kind of numbers are these? I mean, these are integer numbers, so they have some meaning. Well, if you're in 2-dimensional, if you're talking about integer monopole effect, these are precisely Thoules's sigma xy numbers. In fact, Thoules was the first to point it out in his 1985 paper with New and Wolf, although they pointed it in the appendix to their paper just to say, look, we can find the sigma xy as some Chern number in terms of block waves, but you can also construct them out of Green's functions, and this is the way how you do it. So you can prove that in 2D it's the same. But you can also write it in 4D, 6D, 8D, for little d, or any odd number of big Ds. And so this expression was subsequently used by Volevik, mostly in application to PUA superconductors in the 80s and 90s. And so I should say that Volevik did a lot of work on this before topological insulators became popular. And so instead of working with these Chern numbers and block waves, you can write down these expressions in terms of Green's functions. And these are topological. I mean, you can check, for example, this has to be an integer with appropriate normalization in front. So one thing you can ask me, well, or one thing I should tell you.
What's the integration domain there?
Which integration?
In the integral. There.
In the integral?
Yeah.
Over frequency and momentum?
All space?
All space, yes. You integrate over the entire space. One great thing about this expression is that you can turn on interactions, but there are still Green's functions even in the presence of interaction. There is a general mathematical theorem tells you it's an integer, so it has to be an integer even in the presence of interactions. Now there's a little caveat, which is in the presence of interactions in 2 dimensions in integer monopole effect, it's no longer sigma xy. When sigma xy is response, it's given by 2-particle object, it's not a single particle object. So it has nothing to do with response, but it's still an integer. And what I'm going to tell you next, hopefully if I don't run out of time, is that this integer is not just a mathematical number which exists even in the presence of interactions, but it has something to do with real physics. Okay, let's see. So before I say anything else, I want to tell you about the meaning of this invariant if I have 0 spatial dimensions, just one time. And actually, I do want to go back. There's something I forgot to mention. Even though this expression is written in big D-dimensional space-time, even if I live in some, let's say, 5-dimensional space-time, I can always write this expression in reduced dimensionality by simply removing some of the derivatives and just keeping some of the momenta out of the picture. And that turns out to be useful. Even more, if I'm in 5-dimensional time, it's still possible to give meaning to this expression in high-dimensional space by treating some of the momenta not as momenta but as external parameters with respect to which we have pumping. It's tau, this is a picture of pumping. But this I don't want to talk more
So
about.
for the case when the Hamiltonian is time independent, I think in general you can always reduce to the case by integrating out the frequency space. So you can express those into Hamiltonian.
So here you can reduce, for example, in two
If the Hamiltonian
dimensions,
is time independent.
if you have time independent Hamiltonian, if you integrate over frequency, you can prove it goes back to that Chern expression.
Yeah.
Yes, that's true. In case where there are no interactions, by the way. If there are interactions,
Oh,
you
yeah.
can only do this.
Then it's more like a using Lagrange.
Yep. Okay. But so let me talk about this invariant in zero-dimensional space, which doesn't mean that we have to be in zero spatial dimensions. It could mean that we are in arbitrary dimensional space. It's just that I don't want to integrate over, or rather, I mean, I will integrate over the momenta, but it's enclosed in this trace. I mean, this will be ijji here. And so this kind of invariant, Volovi called it N1, and in general he called NZ, those odd-dimensional space-time invariants. And so this invariant N1 has a very simple meaning. So, well, first of all, it can be written in this form. And second, well, we know that G is this, so determinant of G is this thing, where epsilon n has single energy levels. And so you just plug it in here and calculate. It's a sum of signs of all single energy levels. And so in particular, what it tells us is that if we vary some parameter in our Hamiltonian, and if epsilon n move around in some way, and if none of them cross zero, N1 will never change, because N1 is the difference between positive and negative energy levels. And remember, positive energy levels are the ones which are empty in the many-body picture, and the negative energy levels are the ones which are full. So that kind of tells us that if we don't close the gap, N1 never changes, which is something we expected. Okay, so finally we're coming to something new.
I'm sorry. Hamiltonian is, in order to use quantum mechanics, is defined up to a constant. So zero is undefined.
What is undefined?
The Hamiltonian, in order to use the quantum mechanics, you can shift it arbitrarily up and down.
Well, but we're talking about many-body systems, so zero is where chemical potential is. So you do have some memory of where zero sits. So zero is defined in such a way that it's a grand canonical Hamiltonian, if you wish, h minus mu n.
Okay.
Everything above zero is empty, everything below zero is full. So that's how we'll understand it from now on. Okay, so now what about chiral insulators which are in odd-dimensional space, even-dimensional space-time? Turns out nobody has constructed these topological invariants out of Green's functions, and when I realized that it might be important, I decided to do it. So we have to do something different. So one of the things which chiral symmetry imposes, it tells you that number of positive and negative energy levels has to be the same because there is a symmetry between them. And so the invariant N1 I showed to you before is actually identically zero. It's how many positive and negative levels you have. And in fact, all of those invariants I showed to you before, they only exist in odd-dimensional space-time. So they're zero in even-dimensional space-time when we have chiral symmetry. But there's a completely different type of invariant. You can write it down in terms of Green's functions. It was actually written by people working on these problems, but in terms of block waves, in the same way how Thales wrote his invariant in terms of block waves. But nobody has written that in terms of Green's functions. So it turns out to do it, you have to introduce a Q matrix, which is this object out of the Green's function, with sigma being this defining object from the chiral insulators. And you construct this kind of thing, which is also a topological invariant. And here, integration of frequencies over only positive frequencies.
The second, is it capital omega or little omega?
Where is capital? Oh, it's a typo. There's no capital omegas in this talk. It's a little omega. It's a typo. It's typo. Yeah, it will be hard, but I'll try.
Other option is that we hybridization of the question session with lunch.
I have many questions. So
Can we ask the food center to be here?
huh?
Deliver the food here.
Yeah, okay. So, yeah, we can deliver the food here. So, let me just tell you briefly about the meaning of this invariant. Many people know about this kind of invariant, constructed out of a unit length vector n. It's a Skerman number. So, if you have a vector n which has unit length, which lives in two-dimensional space, and if you construct this object, it tells you whether all these n's are polarized, in which case I2 is 0. But if n's have this feature when they point up in the center and down, I guess get down in the center, up in the corners, and there's this Skerman kind of thing, you calculate I2, you're going to get 1 with appropriate normalization, which I think is 8 pi or 8 pi squared. And so this is a generalization of that to higher order objects. So Q is now a matrix, but the square is still 1, as you can check. It can be written in any even dimensional space. This is usually called Hopf term, so this is Hopf term generalized to higher number of dimensions and bigger objects, not just vectors but matrices. And so it turns out this is precisely what characterizes such chiral insulators. And in particular, we can think of a minimum of this invariant when there is not even time. Big D is 0. So if you recall the expression I had on the previous slide, it would be just trace of Q, which is trace of sigma, which is the difference between right and left 0 modes. Because sigma, when it acts on 0 modes, gives you the plus or the minus 1. And so this is precisely what Singer's theorem tells you has to be a topological invariant. And then, but then there are, of course, you can increase dimensionality by 2 and keep writing these invariants in high and high number of dimensions. Okay, now, because again, chiral insulators seem to be important in this whole thing, because as a counterexample to non-chiral insulators, let me bring up this Schrieffer-Higgers example in a little bit more detail. So imagine I have a particle moving along a line with hopping amplitudes T1 moving in one direction, and T1 and T2, which alternate, T1, T2, T1, T2, and so on. This will be the Hamiltonian, which I'll have to write. And so you can work out that the invariant I gave to you in the previous slide can be reduced to this integral. And so what this integral does, it measures whether T1 plus T2 e to the ik, plotted in the complex plane of this number, whether it circles around 0, it doesn't circle around 0. So if T1 and T2 are real and T2 is bigger than T1, then this has to circle around 0, and then this number is 1. And if T1 is less, then this number is 0. So there's two distinct topological classes of such topological insulator. And in particular, you can see right away that the H states exist in one of these two sectors. If you draw, if you write down Schrödinger equation following from this Hamiltonian, and you write down for 0 energy state, this is the solution. The solution has to decay into the bulk as x is increasing, and only this when T1 is less than T2, which is in the state in this sector where I2 is 1. If I2 is 0, it doesn't exist, so there's no H state. Okay, and so finally, this would be something which is some of the more important thing which I would like to tell you, which is, well, okay, there are these topological invariants, but why are they useful, and why is it good to know them in terms of Green's functions? Well, one thing is, in some sense, maybe it's more intuitive to calculate them in terms of Green's functions instead of in terms of band structure, but there is more. We can directly relate and prove the existence of H states in all these topological insulators just by using these topological invariants. It was first shown by Volevik in 2 dimensions for superconductors, but it can, as it turns out, it can be generalized for all of these guys. And so first I'll go over what Volevik did. So he was in 2 dimensions, and he concentrated really on superconductors, so he was here. But this guy and this guy, which are kind of they're characterized by the same topological invariant, they fall under the same category as well. And so what Volevik suggested to do in the work, which I could only find in his book, as a book, Universe in Helium Droplet, very thick book with lots of stuff, so it's kind of hard to read. But somewhere within this book, on some page, this derivation is hidden, and that's kind of like a gem, which is very useful to find in that book. So he imagined a situation when you are in 2 dimensions, and there is a direction S along which my system changes. Maybe I'm an integer clone Hall effect here with sigma x1 being 1, and here sigma x1 is 2, for example. Or maybe it's 0 even. And so topological invariant here is equal to NL, n left, and here it's equal to n right. And let's prove that there must be H states moving along this boundary. So how do we prove it? So here is the derivation. So first of all, we should realize that there is no translational invariance in the S direction, because things change as I move along S direction. So the Green's function along S direction has to depend independently on 2 coordinates, not on the difference of coordinates, as usually Green's functions do in the presence of translational invariance. But in the X direction, it only depends on the momentum. And so now an important object which I'd like to construct is the inverse Green's function, which I'll call K, and it'll be important in what follows. And now let's construct the simplest topological invariant, the one which was kind of 0-dimensional topological invariant. It's a trace of G minus 1 d omega G, which we know is equal to the difference between positive and negative energy levels. But let's construct it at a fixed px. Px is momentum along this direction. And then what we should calculate is the number, this number n1, at some large positive px and at some large negative px. And if there is a 0 mode which crosses 0 as a function of px, the number n1 must change, because there are more positive energy levels here than there are positive energy levels here. And so this is a number which will tell us if we have any kind of branch of excitations which cross 0 as a function of momentum along the edge. And so finally, well, let's write down this expression. Let's show that it's equal to the difference of the topological invariance on both sides here.
So it's number capital.
Huh?
Not the capital here.
Capital. Where did I have a capital? Oh, yes. It's a kind of like a momentum cutoff capital. So some big positive momentum, some big negative momentum.
So it is
And
px.
Well, it's a value of px. So this depends on px. And this is the difference of this object at px being large positive and large negative. And that difference tells me whether anybody as a function of px cross 0.
But you might have high energy functions or levels which go beyond lambda, to the left or right.
But
that can influence the M1.
I also didn't, well, then I didn't understand. So if there's anything above 0, it'll stay above 0. If anything below 0, it'll stay below 0. So it won't change in lambda.
The states only between minus lambda and lambda.
Right. You're saying maybe here there is more stuff going on.
There might be states beyond
Yeah,
lambda, left and right, and that can influence the value of the invariant.
That's true. And there is some subtlety having to do with this, how to choose lambda, which basically I don't have time to go into this, but I know what to do in this situation. There are ways to avoid it. Basically, as a crude way of saying this, just choose such lambdas to make sure that nothing happens beyond this lambda, very large lambda. There's another question, what happens when you're on the lattice, when, px is actually a compact coordinate. But anyway, there are ways to resolve this issue. Okay, and so finally, so this is maybe the most technical part of everything which I have to say. Well, I ran out of time, so you can stop me at any time, but I don't know.
Yeah, we will have more questions, so all the questions will be taken at lunch.
Yeah, okay, that would be maybe the way to do it. So, I apologize because I have to explain it in a technical way, but I want to give you a flavor of how this is done so that you will believe me that if you can do it not only in 2D, but any number of dimensions for all of these symmetry classes. So you should introduce, according to Wolodyk, a Wigner transformed Green's function defined here, so which depends on both momentum and kind of center of mass position, average position of these 2 points. And then you can define G minus 1, which is not the honest inverse of G. It's rather kind of naive inverse of G. So if G is independent of S, which I have translation invariance, then this is the same as honest inverse of G. But this is kind of like a naive inverse of G. And an honest inverse of G is related to the naive inverse of G by means of so-called gradient expansion, which is known in the literature. So you can look it up. And so what you do then is you say, well, okay, but this N1 has to do with this honest K. I'll plug in this gradient expansion, and then I'll work, and then I can show that the difference of these N1s on the left and on the right can be thought of as a flux of this kind of interesting vector whose divergence is 0. And finally, with a little bit of work, you can massage this into a form which tells you precisely the difference. But we can see that already that once you substitute this, you do get something which looks like a topological invariant because it has 3 derivatives. G minus 1 dg, G minus 1 dg, G minus 1 dg. So with a little bit of work, it becomes the difference of these 2 topological invariants on left side and right side. And so basically it proves this, at least in 2 dimensions, for example, for integer wormhole effect. Now there are other proofs in the literature relying on response and Laughlin type arguments, but they're all hard to generalize. My understanding that people are still debating whether they always work. This argument seems to work. It's just pure math. Gives you that H states are there. So it turns out, something which I derived is that you can do the same thing for chiral classes, but in odd dimensionality of space. So there is a 0 mode always if the topological invariant changes. Well, I'm not going to go into details, but with a little bit of work to show that number of such 0 modes has to do with the difference of this topological invariance. Now let's see. Finally, I just want to advertise that now we have a proof, I believe, for all classes and all dimensionalities, and even in the case where topological invariant is Z2, we have to do a little bit more. You can still show that if it changes, you have H states. It's a very nice proof, which doesn't rely on response, doesn't rely on anything, which is directly from Green's functions. So that's already kind of nice. But the most interesting thing, of course, is what happens if I do turn on interactions. And so here, it turns out that it's not that difficult to understand what happens. Let's look at it on the example of this topological invariant, which is the difference of positive and negative energy levels. Suppose I turn on interactions. Well, then the Green's function is no longer as simple as just inverse Hamiltonian. It's given, in general, by this formula, so-called spectral decomposition of this Green's function. And if we look at this expression, it sort of looks like something which looks like matrix elements times these poles times some other matrix elements. But this guy is not square, so the H is the total number of excited states I can have in my system, which is huge. While the F is total number of creation and annihilation operators I have in my system, which in general is not as big as the H. For non-interacting system, dh must be equal to df, and these are all square matrices. But for interacting system, dh is always larger than df because when I create things, I can create particle Hall excitations. So there are more ways to create excited states than just by accident by creation operators once on the ground states. And so you can prove that the determinant of Green's function acquires additional zeros in addition to poles. So instead of having this formula, you have this formula. Basically, without interaction, you have a certain number of poles. With interaction, you have additional poles having to do with all these additional states with particle Hall excitations, plus zeros, because total power of G should not change. If omega is taken to infinity, G has to go as 1 over omega to some power. Actually, G itself, 1 over omega, the determinant of G is 1 over omega to some power. That power doesn't change, and it's equal to the number of creation operators. Anyway, so for each extra pole you earn once you turn on interaction, you also earn a zero. And now, once you understand that, you see how topological N1 changes. Basically, instead of just counting signs of poles, it also counts signs of zeros. And that leads us to say that, well, we can be in the following situation. Suppose I change some parameter and the energy of some state changes according to this red line. For example, I'm changing momentum along my defect, and it changes like this. And then I turn on interactions, and a pole and a zero can appear, such that if they coincide, they would cancel, and I go back to non-interaction formula, but now they split a little bit. And then I crank up interactions even more, and the pole moves, and eventually annihilates my zero, and so now, well, zero moves, annihilates my pole. So now instead of having a pole crossing zero, I have a zero crossing zero. In other words, I don't have any H states, but still the topological invariant on left and right side are going to be different. And so it tells me that somehow in the presence of interactions, I may go from one topological state to another without ever closing the gap. Instead, I have zeros moving around. But the poles don't move around. It's a very strange conclusion, but it turns out that it's not empty math. There's already a good example of this.
Does the imaginary part of self-energy play any role? Which we have some relaxation, which you wouldn't have in a non-interacting system.
Well, sure. I mean, self-energy does play a role, but I don't have a good way of telling you right now exactly, what you should look for in self-energy to see that zeros are there. But we can talk about it. Right? So far, it's a very general statement, true for any interacting systems. And so this will be the final thing which I wanted to say, which is there exists a model due to Kitaev, which Kitaev invented about a year ago. It's a one-dimensional model in the symmetry class of Su, Higger, Schrieffer, soliton, which in the presence of interactions can go from one topological state to another without ever closing the gap. And so the way he constructed his model, it's a particle fermion which hops along one-dimensional line with hopping which alternates. One is smaller, one is bigger. But it's not just one fermion, it has to be 4 fermions. Now, why 4? Don't ask me. Kitaev invented it. He also proved that you must have a number of fermions which is multiple of 4, which I don't quite understand. And so he also added interactions. This is some generic quartic Hubbard-like interactions. However, writing them on this slide would have taken me the whole slide. You really have to be a Kitaev to be able to invent such interaction. Basically, it's one of the things which don't try it at home. So I'm not going to write this interaction. But that was one thing about this interaction was that Kitaev could actually exactly solve this model in the presence of those interactions. And what he showed is that if you don't turn on interactions, and if you go from a regime when T1 is greater than T2 and T1 is less than T2, you go from one topological class to the other, as I've already demonstrated. But if you do, and you have a phase transition exactly when T1 is equal to T2, this, by the way, is in the plane of T1, T2, the line here, at which there is the bound gap actually closes. This is very easy to check.
Those real?
Huh?
It could be complex.
In this case, there would be real. Now, there could be complex also. But in fact, for Kitaev, it was important they were real. If they're complex?
Yeah.
Well, in the complex, you should plot here absolute values of T1 and T2. But in any case, for Kitaev, for his interactions, it was important that they're real, so let's make them real. For the fact that these are two topological classes, it doesn't matter. It's real or complex. Well, let's not talk about complex, since especially Igor really wants me to finish soon. So, but you can check. It's without this interaction, it's a very simple problem. So you find that the gap closes when T1 is equal to T2. But what Kitaev showed, if you do turn on interactions and you go along this path, then the gap never closes. In fact, the way he showed it is because as you move along the line, T2 is 0, and it's really a bunch of disconnected double sides, so you can actually solve it quite brute force. You don't have to do anything sophisticated to show it. Well, but he never explained why that happens. He just said, look, I did this calculation, and it happens. Actually, I will take my words back. He has subsequent paper, and then there's another paper by Erisberg and his collaborators, which shows using the language of matrix product states. So there's a reason why that happens. But that language is very specific to 1D, and I don't quite understand it. So I wanted to understand it in some other way, which would be more clear to me. And so what Andrew Essed and I checked recently is that the Green's function actually has a 0 at 0 energy exactly at this point. So if you move along this line, the gap closes and then opens up. But if you move along this line, the gap doesn't close. Instead, a 0 kind of separates from the conduction bands, moves towards the 0, and then goes back and merges into conduction bands. So that's precisely the mechanism which I have described, although I don't know why it happens in this model, and I don't have a prescription of which kind of models this can happen and which kind of models this cannot happen. And so basically, finally, I come to my conclusions. So first of all, single particle Green's functions give you an alternative way of looking at topological insulators. Seem to be powerful. Like if, for example, you're doing numerics, to me, it's not kind of a natural object to compute. And out of this object, you can check whether something is topological or not simply by looking at this topological invariance. And the second message is zeros of Green's functions. Clearly, they play a role. Here's an example of a one-dimensional model where they somehow screw up topological properties. So what are these beasts? What is the zero of Green's function? Can they be measured experimentally, for example, with angular resolve photo emission? Do they play any role beyond changing this topological invariant and removing some poles? So basically, I think, as far as I can tell, this kind of set of questions is big and wide open. I would add maybe to this also how this matches to the other efforts which other people are doing, having to do with computing responses of topological insulators to perturbations, and because responses are not single particle property, and they're also quantized in some sense, even in the presence of interactions. But here I also have something which is quantized in the presence of interactions, but presumably not equal to those responses. So what does it all mean? So all of these are open questions. So let me stop here.
Let's have a question session on the way to restaurant. So we are few now. So let's just split between two restaurants. So are you going?
People can go wherever they want.
Oh yeah. So
Just follow some people and just go what type of restaurant you want.
yeah, exactly. But just remember that the next talk is 10 minutes past 2.